Okay, so we're going to start this workshop, okay? So thank you everybody for coming to the Midokura's workshop, and thanks to the HackUPC organization for having us here. So we are Victor Badenas and myself, Estela Vasquez, and we are going to present a workshop called Fine-Tuning Computer Vision Models for Edge AI Applications. So we are part of Midokura, which is a company in the Sony group. So the Midokura company was born in Japan some years ago, and then Sony bought it, and we began to develop its AI applications. So basically, we will be explaining you a bit of what we do in the product of AI. So the company has different products, and one of them is the Edge AI product that Victor and I, we are part of the AI teams in the company, and we will be explaining you them. We do not have a challenge in this hackathon, but we will be here to be supporting you if you have any doubts in other challenges. Okay? So let's just start. We are going to be talking about first computer vision applications in general, and then how to retrain, what is retraining a computer vision model and how do we do it, how to deploy an AI model on an edge device, and what is an edge device, and then we will show you a bit of a demo of an application that we created, which is license plate reading. Okay? Then Victor will be showing a small hands-on, so practically how to program these processes of having a model, retraining, and not the part of deploying on the edge, I think. But it will be like the first part of it, and we will have some time for the Q&A, okay? So, first, when you want to build an AI application, a computer vision application in general, and deploy it on the edge, you need basically three things. So you need the data to train the model, so both the images and the annotations, for example, in a JSON format or whatever. So if you are going to, for example, build a detector, if you want to detect people in the image, you need images where people is there and the annotation, so where is the person. This is an issue because gathering all this data and all this annotation is costly in terms of time and money, so the data in general is scarce. Apart from the data, the images and annotations, you will need the computer vision model itself. So in general, you implement a deep neural network and you train it, right? And finally, in our case, we are deploying these models on the edge, so you need an edge device. An edge device basically is a small device with some constraints, both memory constraints, format constraints, and so on, that it's working on the edge. So we try to bring the AI model working to the edge, so near to the user, so that it can work offline in a small device. You don't need to connect to the cloud, so the privacy is increased there because you don't need to send the images to a server, you don't need to share them. And also, since it's in a small device, it's really fast, so you can obtain real-time predictions and you can have real-time. The issue with the data is that, as I commented, obtaining good quality data is costly in terms of time and money, right? So to deploy an AI application in general, you only will have a small quantity of data. So if you want to have an application for a retail, okay, you have some images of your retail store and some annotations, but you won't have huge quantities of data. And usually to train these deep neural networks, you need huge quantities of data. So for that, in Midokura, one of the products that we have is a retraining service, right? Where you can take models that are already pre-trained with some general knowledge, and with your small quantity of data, you can retrain them to adapt them to your specific use case, right? So how do we do this process? For retraining a computer vision model, we have this baseline, this starting point, that is the AI model. So it's the architecture of the model, but it's uninitialized in terms that there is no knowledge in this model. You just have the architecture. You build the layers and the neurons and so on, but there is no knowledge there. And the final goal is to have this AI model fine-tuned so that it can solve your particular problem, right? So, starting from there, from the uninitialized model, how do we arrive to the AI model for your use case? So, what we do is, first, we have a big general data set. For example, in computer vision, there are different data sets that are huge, like more than, I don't know, 1.5 million of images, right? So there are, for example, ImageNet, or Vogue, or Coco datasets that are open source, are public, are like, they were generated through the years by the collaboration of a lot of developers and so on. So with these datasets, we are able to obtain a pre-trained AI model with some general knowledge of it. So for example, in Hugging Face, there are lots of pre-trained models of transformers, of computer vision models, and you can find pre-trained models out there, right? So once that we have this pre-trained model and we want to adapt it to our particular use case, we can, using this small data set, the particular for the use case, that the user provides, so the person that wants to create this AI model for this particular use case have a small data set. And with this small data set, we in Midokura offer this easy retraining platform where you can use transfer learning to run this retraining process. So the tool that we build is this retraining service that anyone can use. So if you have a store and you want to deploy AI models in your cameras, you don't need to have AI knowledge to build this model, right? We offer you pre-trained models and the method to retrain them, to finally have the fine-tuned model. And then, once the fine-tuned model is obtained, how to put it on the cameras, right? So, to deploy this model on the edge, we start from the AI model that is already adapted to your use case, and the goal would be to introduce this AI model and to deploy it on the edge device to solve this problem offline and in real time. These edge devices have a lot of constraints, as I said, in memory and format, right? So, to change the format of this model and decrease the size to fit these constraints, we run two steps. First, we quantize it. So we have the quantized model that is already pretty much smaller than the original one. Basically, quantization, for those of you who don't know what is it, usually this AI model, this neural network, use real numbers, right? So floating numbers with decimals. And when you apply quantization, you convert these weights, these numbers that are in the neural network, to integers. So instead of using real numbers, you use integer numbers, and so the size of the model is much smaller. There is usually a loss in performance there, but with the techniques we apply to quantizing, we try to minimize this loss in performance. And then we also convert the model to fit the format that the device needs, and then we can finally deploy it, yes, right? So this application that we did consisted of reading license plates. If you have a camera on a parking, if you want to enter, the door can automatically open or be closed for you reading your license plate. So we deployed a detection model that detected license plates in an image in this small sensor, in this edge device. And after this detector of license plate was applied, having the image, the crop of the license plate, we ran another neural network that detected the characters themselves. So here we are reading a Japanese license plate that contain a lot of kanjis and hiraganas. So there are more than 170 categories there. It's not as simple as our license plates here in Spain. And we also pre-train this model and retrain it to be adapted to this problem. So finally, once that we have this string of what is the content of the license plate, using the IoT platform, that is the other product of Midokura. So we do this AI system, retraining system, and then other team in Midokura is building this IoT platform. So you can obtain in an IoT platform in your mobile phone or whatever the result of this model that is running on the camera. And I wanted to share with you this video that is 1 minute long that shows a bit what we do. So this is our fancy office. And we set there a camera and this license plate. So it's a synthetic license plate that we generated and printed. Just that. And I don't know if you see it clearly, but there are some patches. So to check that the application works correctly, we just crop patches and stick them there and put them out. So as we change the patches, we can see that the string, like the license plate reading that appears in the IoT platform is changing as we do these changes in the patches. So the model works correctly and is deploying this small camera in real time, giving predictions in real time. And that's it for my part.
Did you create the data yourself, or it was already some?
In this case, it was a mix of synthetic data that we created our own, and then we have a small data set that a user gave us. So there was some user interested in this application, and they gave us like 200 images, something like that. And they were not really bright and kind of blurry. So we created another dataset that was synthetic one, and we mixed them to retrain the model. Yeah. Thank you for the question. And
well, the goal of the examples that we wanted to show is basically the two slides that Estela showed here, right here, which are coming from a baseline model, just with random weights without any knowledge being acquired by the model, and then retrain it so that you have a neural network that has general knowledge and then goes into the fine-tuning stage so that you can adapt this general model onto a specific task. This is the first part, and the second part that I will be showing on a notebook that you have in case you're interested on the code. It's on the Midokura channel on Slack. We have shared it so that you can clone it. It's a Jupyter notebook on Colab, so that you can run it over there if you want to. It's very academic, but the goal was to showcase a little bit of the process of what we do in Midokura with other kinds of data, which probably we cannot share here. And the step about quantization. We are not going to go on to over the format conversion, basically because that part is it's proprietary, so we are not going to go into that one. And then I go into this. Maybe it's a little bit too small, right? Okay. So it's nothing fancy. It's something just to have a little bit of a more hands-on context about what we do. But basically, the goal here is in this notebook, what we're gonna do is getting a simple, or not a simple model, but a well-known model known as Mobile92, which is a quite small, relatively. Model which is very commonly used for creating small models for deploying in applications that require this kind of smaller models, and we're going to get some pre-trained model which is already available on Keras, but as Stella said, you can find pre-trained models for a whole bunch of tasks, even if they are time series data analysis or whatever. Usually HackUPC is a very good place to start. They have license though, they have some licenses though, so I would be careful with that. And the first idea is to get a data set that the network was not pre-trained with. So, for example, in this case, it's, as I said, it's very academic. We will be using some different sort of other sorts of data, but in this case, we'll be using. Oh, no, that's not what I wanted to do. Thank you. We'll be using the Caltech 101 dataset, which is basically a classification dataset, for which, if you don't know, classification dataset is a dataset where the annotation basically consists of a category. So you're getting an image and you're classifying it as a dog or a cat. So 0 or 1 being encoded as an image, and that's it. And in this case, we're going to have 101. We're going to have 101 classes. And well, this is just a downloading code, but the idea is to be using, for example, in this case, we are using some Keras utilities that basically are classes that allow you to not load the whole data set into memory, but instead of that, to not overflow, like to not have your laptop explode of RAM usage. Reads the images from a directory in a streaming fashion, so that it basically a generator that we keep asking it into an iterating loop, and that's it. And it starts giving you batches of images, which basically are stacks of images, so that you can parallelize computing in training. Also, some worthy things to say is that we are using the built-in MobileNet per process input function, which basically scales down, like it subtracts the mean of the whole data set for which the network was pre-trained with, and also scales it down from integers, so 0 to 55 to -1, 1, which are the values that usually a floating point network usually is comfortable working with, and it does. And we do a validation split so that we can evaluate how the model performs with data that they have not seen. Maybe I'm explaining things that are a little bit too obvious. So if I do, please raise your hand, and I will skip stuff.
It's saying no, so.
Huh?
It's saying no.
Okay. Then we start going into the creation of the model. So basically, we are gonna use a model that is predefined in Keras, because we don't have time to generate a model from scratch. And this is the MobileNet V2, and it's as simple as just stating that you're gonna use the weights in ImageNet, so that they're gonna do a request on the API. I get the pre-trained models for that data set, and it's going to load them, and it's going to work right out of the box. What's the problem with that? ImageNet does not have 101 classes, but rather it has 1,000, typically. And the classes are not the same. So, for example, maybe in ImageNet you have butterflies to be classified. That's an actual class on the data set. And maybe in Caltech you don't have that. You may have another one. So you need to adapt that model to work for that data set. So in order to work for that data set, what we do is we preserve all the backbone of the model, which is basically all the layers that have learned textures and that have learned some context on that, and you only replace the last part of the network, which is basically what classifies. So what gets all the information, all the knowledge extracted from the network, and outputs it into a feature vector that you can get the classes for. Basically, it's a vector of n positions, where each one of them has a probability of being of that class. That's it. It's not an amazingly complex part. So in that sense, what we are doing is replacing the layer that has that vector and that outputs that vector of 1,000 classes into one that only has 101. And this is like this line right here, right? And then we create a model where we are getting from the input layer, which is the input of the backbone, and then just creating a model with the new classification layer, with the new classes that we need. Next step. We don't want the network to learn like the backbone, we don't want it to change. We already know that that's general knowledge and it works. The only thing that we want to train is the part that we're added in the end. So in order to do that, you basically set all layers to trainable, except for the last one. So maybe not the previous code, but it works. And then that's something from Keras. You need to compile the model so that you set it to which loss you want to use. So basically, which is the metric that is gonna make the model know if the model is good enough, like make the training loops know if the model is good enough or not, and how much it should change in order to be good or not. And also metric, so in this case accuracy, which is basically a human readable metric that we humans we know what it means, because knowing categorical cross entropy, I don't know if you can or can't, so that's fine. And then here you can print which is the summary. These are all the layers that are going to be in our model. All of these are not going to be trained. All of these are general knowledge that are already being trained by ImageNet. They are up. And then there's the last one, which is the one that we added, that is from here to here, from this embedding that is the knowledge extracted by the whole network until the number of classes that we want. We're only going to train this. This dramatically speeds up the training process, because you're not training 50 layers maybe, and you're only training the last one. Then we go on to training, which is very, very easy thanks to Keras. We only give it the train generator and the validation generator, and for how many epochs, so how many runs over the whole data we want the model to train for, and also a number of threads in order to load the data faster. But that's not relevant. And as you can see, like the model trains quite fast. I'm not going to run it now for because it will output exactly the same thing for similar, so it has no value to it. But it's like 30 seconds for the whole work, going for over 1,000 images more or less. So that's quite fast. And just by going once over the data, we already have a 90% accuracy. I mean, that's because we are relying on all the knowledge that is being learned before by ImageNet and only doing the last part, right? And in 4 epochs, we are in a 95% accuracy, which is quite comfortably something to be good enough. Then that's just some plugin for the metrics and the accuracy over some. Yeah.
Are you training just the last layer that you added, or also the previous one?
Yeah, I'm only training the last layer. So the last fully connected layer, which basically recombines it, that's the only one that we are training. We are not, because just the last one, I think it's an average pooling, so we're basically extracting from all the different channels and just aggregating into one single feature vector, which it's not trainable. And all the convolutional layers that come beforehand, we expect that to be trained correctly with ImageNet. Like the domains are not so different between the ImageNet and the Caltech dataset, so that we don't need to unfreeze more layers. If the accuracy here was not good enough, probably the domains, that means that the domains diverged a lot, and maybe unfreezing some of the layers like before the fully connected would have been required. But for this simple test, that was good enough. Does that answer?
May I say one comment?
Yeah, sure.
For example, if you use ImageNet, I don't know if you're familiar with the dataset, but it has like a bunch of classes. If you want to deploy an AI application to solve a problem such as the housing problem the housing challenge that was presented, like living rooms, terrace, and so on, like it's a really particular domain, so the domains are different. In that case, you might need to retrain other layers.
Yeah.
So basically, your data set has the plates and labels as the name and numbers.
If we're talking about the example that they,
So you're doing trying this model that did you talk to, I don't know, the code of the image, because the size is the same for all the plates as I know. So in a country, size of the plate and size of the number and letter are the same. So in that case, did you try, I don't know, maybe fast RCNN, something like this, just like catch the ROIs, regional interests, and I think like 94% was just increased to.
Fast RCNN is a really large network that will not fit in the SDIs that here. That's a first point. And then here, of course, this is a demo that we prepared for this workshop. Like if we are working with classification problems as this one, we would not be happy with 94% of accuracy, but it was just in 2 minutes that we trained. And moreover, the license plate recognition problem was a detection one, not a classification one. So instead of just having one label per image, you have like the bounding boxes that detect where each object is in the image and which class is it. So here, for example, you have like the bounding box for the candy, the bounding box for the street, same is a street, the bounding box for the two, same is a two, and so on.
In the classification network, you're only gonna have the class for that. But in this sense, what you're gonna have is probably the output of the network is gonna have something to do. Probably you're gonna have to post-process at some point, but it's gonna represent the coordinates for the four bounding box points, or maybe even an X, Y, and then a height and width. But that's a coding problem. But they differ to different tasks.
What is the size of a model in an edge device?
Okay. So the edge device that we were using here, that is the IMX500, is a Sony intelligent vision sensor, and the memory constraint that it has is 8 megabytes. So the size of the model, at most, it can be 7.5 megabytes.
You also have to take into account for the image.
Another process running into the device. And usually, I'm not familiar with the fast RCNN that much, but the same model that we implemented for the license plate recognition, before passing on this quantization and conversion process, it was like 40 megabytes. And after quantizing it and changing the format, it was 5.5 or something like that. So we fitted the device.
I was at some point.
Thank you for the question.
That was actually the next step. So the next step for the mobile network we are going to get at is that we are going. The model is going to be around 10 megabytes. That's a little bit smaller than what Estela just said, but it's around that. And then what we do for as we said, is quantizing the model. So basically, there are different types of quantization. I've added here links because I probably don't have time to explain the difference between post-training quantization and quantization aware training. But these are resources from TensorFlow that are very well explained and have all the information that you need. And basically, as Estela said, going from floating point weights. So all the layers usually go into floating points. We are going to quantize them into usually in-date format. So in that case, we're going to have a discrete number of levels for each of the weights. And that means that the amount of knowledge that each neuron is able to absorb, it will drastically decrease. So in post-training quantization, what you usually do is you try to have the best possible range of floating point values represented by the in-date format. But in the case of quantization aware training, what you are doing is retraining the model while being converted into int, so that you are able to adapt the whole pipeline of the model to that new format. So usually quantization aware training is way costlier, but it usually yields a little bit better results. In this case, what we did here is basically we did a post-training quantization using TF-Lite, which is a very well-known format for sizing down the models, especially taking out the optimizers and converting it to a protobuf format so that it can be read from any kind of device. And usually TF-Lite has interpreters in different languages. So for example, in embedded devices, you would use, for example, Rust or C. It has bindings for that, so that you could load the model directly there. And here it's very similar, like it's following the documentation on TensorFlow. It's not and here you convert the model, setting the internal operations to int8. What does that make? This makes so that if you get an interpreter and you load that model and you get the data type for each one of the layers, this is the layer name, but never mind. We have set the input to be floating point so that we can load an image at this floating point normally, but it's going to quantize it, and every single layer that is on that model now is on int8 or int32. Why int32? Because each layer has a list of supported formats, and the converter tries to get as close as possible to the defined format. So it's not going to be floating, that's for sure, or at least in most of the layers. That's basically it. And the idea that I wanted to say is that after doing the post-training quantization and having the model in int8, we are going from 95%, was it, onto 94.7. Good enough. That for that little effort, that was good enough. And then what I wanted to go is to the size and runtime comparison. Because once we have gone into the intro floating point TF-Lite models, this is more on the TF-Lite conversion model more than on the actual int8 and quantization part. You're going from 66%, from 66 milliseconds of forward time. So for doing a prediction, it's gonna have 60 milliseconds latency. We're going into 16, which is quite nice. And depending on the type of operations that your edge device is tailored to. So, for example, in the IMX, we are tailored more into int8. We require this. We are required to convert into int8 so that the inferences go way faster than if it were to floating point, because it would have to make the conversion. And then the size comparison, which is basically that going from 9 megabytes more or less into 2.7. So 4, 3, more or less. So that it would make it fit into this small devices. And that's it. This notebook is available on the Slack channel, and if you have any questions, please ask us away about it.